All right, so I've identified it. Now what I have to do is I have to write an equation. And the equation that I'm going to write the voltage of the source in terms of the node voltages on either side. So that means that 16 is equal to VD minus VC. Everybody see that? Okay, so this is what I got from this step here. I identified all the supernodes. There's only one because I've only got one voltage source. And I showed it, in this dotted line. And the reason I did the dotted line around it, you'll see in step 5. But for now, you do have to look inside this thing and look at the voltage source and just write that voltage in terms of the voltage on either side, the node voltages on either side. Okay, if this were a dependent voltage source, you would do the exact same thing. The only difference is that instead of just the number 16, you would have some controlling quantity here. But, it's the same exact idea. So don't get thrown off if you see a dependent source, a voltage source. It could be a supernode. All right, so now I'm done with that step, and I love checking it off, because now I'm almost done. The last step, where it says Kirchhoff, I have to write Kirchhoff's laws. So I'm doing node voltage analysis, which means we're talking about nodes, which I think it's obvious that we're probably going to use Kirchhoff's current law. And here's what you have to remember. You want to apply Kirchhoff's current law at all the non-reference nodes. How many non-reference nodes do I have? And for the purpose of this step, this supernode, think of it as a big black dot. Now you can't think of it as a big black dot for the fourth step because you have to look inside and write the voltage of the source in terms of the node voltages on either side. But for step 5, you definitely want to think of it as like a big black dot. It's just a node. I mean, it's a supernode, but it's a node. And so in step 5, I want to write Kirchhoff's current law for all the non-reference nodes. So I'm not going to do Kirchhoff's current law here because that's a reference node. I'll do it here and here. So there's only 2 equations I have to do. And label them. So you're going to do Kirchhoff's current law at node A. And then we're also going to do Kirchhoff's current law. And I could let just so that people know what I'm doing, a supernode. And I guess it's supernode D and C. Okay, so I'm going to do these 2 equations. Let's just do those right now. So at node A, let's see, we've got, okay, I take currents leaving the node as positive, so this will be minus 10Ix. Use that. And then plus, okay, tell me if you agree with me, VA minus 0 over 3. Everybody agree with that? All right. Now, I have an equation that has Ix in it. I don't like that because Ix is not a node voltage. So I go back here, which is what we got in step 3, and I'm going to substitute minus Vc over 2 for Ix. And now I'm happy. And I'm happy because I have an equation that only has node voltages in them. That makes me happy. By the way, this equation that I got in step 4, I'm going to label it as equation 1. And you should remember that the 4th step is the beginning of writing the n equations in n unknowns. So that's why I labeled this one number 1. I didn't label this one because I'm only using this for the purpose of substituting for the controlling quantity in terms of the node voltages. Okay, so this is equation 1. This is equation 2, and now I'm about to write a 3rd equation, which is the Kirchhoff's current law at the other non-reference node, which is the super node here. So what do I have? I've got VC over 2, VC minus 0 over 2, right? Because that's the current leaving here. Okay, so this is a big black dot, right? Minus 0.9 plus 10IX. Equals 0, okay? Let's make sure everybody agrees that that is Kirchhoff's current law at this big black dot.
Doing ins as positives or ins as
No,
negatives?
outs as positive.
Okay, so then the first one isn't it minus?
Well, it would be minus IX, but remember IX was minus VC over 2. So that's why I got VC over 2. Actually, I ignored the IX and I just looked at the voltages here. VC minus VB over 2. Okay, so everybody cool with that equation? And again, I'm not totally happy with it because it's got something in it that's not a node voltage. So I'm going to rewrite it, VC over 2 minus 0.9 plus 10 IX. IX is minus VC over 2 equals 0. There I have equation 3. And I'm really happy because I've got 1, 2, 3 equations in 3 unknowns. Right? What are the unknowns? They are VA, VC, and VD. I skipped VB because VB was the reference. That was 0. So great. I've got 3 equations and 3 unknowns. I can solve for it. I am not going to do that in front of you. And honestly, I do not look at that work on your test. I'd suggest, I mean, if you're not in my class, I don't know what Keith does, but I'd just say, you know you've got 3 equations and 3 unknowns anyway. It does turn out that VA, okay, I don't know what it is. It's 3 volts. VA turns out, you solve these 3 equations and 3 unknowns. And I often show that by dot, 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 you know, math, math, math. And you end up VA is 3 volts. Great. Which, by the way, is exactly what I'm looking for, VOC. So I have found VOC. VOC is 3 volts. I'm halfway there. Remember, I'm looking for, I also need to find the short circuit current. Okay? So I'm going to erase all this because I want room to do that second part of the problem. And you may be tempted to use the same picture because, you know, we all get lazy. We don't want to waste paper, but don't. And the reason you shouldn't do that is because it really is a separate part of the problem. It's a new problem, and things will be different. You can't use the same. I mean, it'll look similar, but it is different. Okay, I got to take off my check marks because we're going to do this method again. The short circuit current is similar to the open circuit voltage, but instead of leaving the terminals A and B open, you short them. There they are. And then you just label a current there, which is the short circuit current. So that's what I'm looking for. Once I find that, then I'm done. Because then I've got RTH, which I erased, but, well, put it back. RTH is just VOC, which we just found, over ISC, which is now what we're looking for. So to find ISC, use figure 2. And I think I'll redraw figure 2 in that same way. You know, getting rid of the corners. Okay, so something's happening here. So we've got this, and then we've got this shorted out. So do I actually need to show that 3 ohms? No. Can I? Because this, it's being shorted out, so a short in parallel with resistor, I mean, you can do the math, you get 0. So the circuit actually now looks like this. So ISC, okay, and this is figure 2, is there. Okay, this was terminal B. I mean, terminal A is here, but now A and B are the same terminal. But I'll keep the others D. Oh, actually, yeah, it's all right. And then C. Okay, so I did label the nodes, but I think just for the heck of it, I'll do mesh current analysis on this one, just so that you can see both of them. All right, so make sure everybody agrees that the picture I have is this circuit shorted out at A and B. Did I miss anything? I make lots of mistakes, so please make sure that I didn't. Okay, so I'm going to find the ISC with this figure, and this time I'll go with mesh current analysis just to do it. Okay, so we're going to do the same steps. Do like the super Kaufmyn. Draw a label, something about dependent sources, something about super something, and Kirchhoff. So draw, we've just drawn it, great. Label, so in this case we want to label the mesh currents. So there's 2 meshes here. So just draw, does he make you always do it counterclockwise or clockwise? Does he care? Always clockwise? Okay. Doesn't really matter, but let's go with it. So, and of course you'll never draw a current without actually labeling it, right? What should I label this one? I suppose I could just call it I1. But there is a current in the circuit